So, welcome everyone to Understanding Ownership in Rust. I've read this chapter but a while ago, so it's going to be quite good. We'll just go through it, and I think it's better if people interrupt and ask questions and do all the usual, let the conversations just naturally flow. So we'll kind of use the book as a rough guide for the conversation, but as always, if we veer off down loads of different avenues, that'll be all the better for it. Definitely learn more that way, especially because you can go home and read the book on your own, but you can't have those conversations when you're at home. So don't be shy. Put me on the spot. I don't really know what I'm talking about. So that's good. So I'll kick it off just by literally reading this through like line by line, so that you can get an introduction to what we're talking about. So ownership is Rust's most unique feature. It enables Rust to make memory safety guarantees without needing a garbage collector. Probably a lot to talk about just in that fact there, but being such a low-level language, it just simply couldn't stand having like this runtime thing that's going around checking all your variables and your pointers and making sure that they're all cleaned up. So Rust doesn't have a garbage collector, meaning that it has to have other ways of managing memory for you. It says, therefore, it's important to understand how ownership works in Rust. And this chapter will talk about ownership as well as several related features, borrowing, slices, and how Rust lays out data in memory. Any questions? Let's go. Next page. I'm just going to flick through so I know what's coming up and preempt things. Stack in a heap. Rules, variable scope. Okay, yeah, so there's some good examples. Memory allocation. Diagrams. Wow, this is a long one actually. There's a lot to go through here. So it's probably best if we do some like high level examples, get some code on the screen, run some code, whilst just using this as a bit of a guide. So otherwise it's just going to be me sitting and reading to you, which is not going to be interesting at all. But let's just start it off and say that all programs have to manage the way they use computers' memory. Some languages have garbage collection that constantly looks for no longer used memory as the program runs. In other languages, the program must explicitly allocate and free the memory. So Rust uses a different approach though. This is what I found interesting, is that it has a system of ownership with a set of rules that the compiler checks at compile time. So really it's making the compiler smarter so that it can essentially write some code for you to do the memory management, which is what's happening behind the scenes. And it says that none of the ownership features slow down your program whilst it's running. So it's a system that helps construct the thing that's going to run in the end, and it has no cost on that. When you understand ownership, though, you'll have a solid foundation for understanding the features that make Rust unique. So this is why we're actually all here, is because it's not just another programming language, it actually has unique features about it. That's why I'm interested in it, especially with WebAssembly and things like that. But yeah, we're all here because it's actually unique. And I think this chapter is probably the ownership and borrowing is the most unique thing about it. So crucial to understand it. Stack and heap. I think we should skip through a lot of this and get some demos, just because make it more interesting. Trying to think, do we need just a little bird's eye view of what the stack and heap is? Maybe we'll get to that in the examples. So let's first look at the ownership rules. Yeah, we're going to work through them to illustrate them anyway. Each value in Rust has a variable called its owner. I think this is the main difference between Rust and other languages. There can only be one owner at a time. And this is the bit that really trips you up when you first learn it, especially if you're just used to doing higher level languages. And when the owner goes out of scope, the value will be dropped.
So that's how it knows when to drop a value.
Yeah.
Because each value has an owner, and you can only have one owner. Therefore, when the owner gets out of scope, it can drop the value. Whereas in C or C++, there's no concept of owner. There are many pointers pointing at the same value. That's why it comes to the developer to clean up the value when you think it's safe.
Yeah.
Whereas I think that's the key to understand that because you have an owner, then you know when the owner is dropped, then the value is dropped.
Yeah, and crucially, that can be done at compile time, right? So it sees a scope or a function body or something like that, and it knows that the rules of Rust and its ownership model. It knows that it can drop a value at the end of that scope, for example. Whereas you don't have to manually do that, although you can, but very rare you ever do that. And we'll get to some examples now. So we've walked through an example in chapter 2 yet. Now we're past the basic syntax. We won't include all the FN mains. That's all right, because I've got my editor here with a really cool theme for us to look at. And as a result, all our examples will be more concise, letting us focus on the actual details. Yep, no problem. And I'm going to type all these out anyway. So let's look at the first example, which seems so simple, right?
Yeah.
What can be so hard about that? Let's say we have a variable like this, and the s refers to a string literal, where the value of the string is hard-coded into the text of our program. The variable is valid from the point in which it's declared until the end of the current scope. Okay, so let's just chat about that first. So in Rust, the scope is like, in this case, when you've just got one function, that is what I've highlighted there is the beginning and end of that scope, right? Correct?
Yeah.
Most of the things I say out loud are going to be questions, by the way, even if they sound like I know what I'm talking about. So let s equals this string. Crucially, it only lives until the end of this function. That will become more why that's important will become apparent in a second. We can actually place this inside another set of curly braces. Let's get rid of some of these comments. This creates a new scope in Rust, in which only the things declared inside it are valid, although it can technically take things from above it and use them inside. But just to make this really concrete, if we try to trusty print line with an S, hey, this isn't going to work. Find value S in the scope. Moved it out and move that inside. Actually will work. Some other things have happened when we did that, which I think we'll get to in a second with like moving of the owner. Actually, yeah, let's make a quiz.
Oh, has it moved?
Yeah, well, that's going to be the quiz, right? Because I literally don't know. What's going to happen? Will this program compile? Who wants to say yes or no? First of all, well, what's happened? Let's think what's happened first.
So it can be two things, I think. It might be that the S has been moved into the scope, in which case S in the outer scope no longer exists.
I personally think that's correct.
Or
I don't know if
I actually don't know, or maybe it's been borrowed. I don't know.
So I think because print line is a macro that looks like moving S, you actually aren't. Case.
Right. Yep. Right. Perfect. So that was not what I expected. So that's good. Special case is in.
So if you did some other operation with S above it, then it wouldn't compile because it would break.
Above where? Sorry, here.
Above the print line in the second scope.
Yeah.
In the other one.
Yeah, so inside of the bracket.
If you did some other operations to it, then it would not compile, right? Because that would verify that it was because of the print line.
So if you make your S mutable and then put S push here.
Can you just push another string like this, or do you have to do push SDR?
Yeah, use push string.
Push SDR.
Yeah.
saying then? I don't know. No, see, that's
to be type string as well, rather than the string size.
yeah, you can't do that. So let's just make that a string.
And that too. Is it? Oh, you need to put a character, is it? Just a character.
No, we need to go back to where we were. That's all.
Okay.
We were correct. It's just that a string slice is like it's immutable, I think. Like from the point it's created. So there you go. See what happens there. Oh wow. Okay.
I think it doesn't get moved. Like the inner scope can just access anything from the outer scope.
Yeah.
It's just fine. It doesn't just move. It doesn't move it.
I think is the point there that it's because it's a macro.
So
So
I think it expands into something that's borrowing S, so there's an ampersand in there that you can't see.
yeah, like an implicit borrow. Let's see if we can make that. If we can prove that. So say greet. Say takes a input. Oh no, we'll take a string. Yes, this should highlight it hopefully. So instead of just printing there, let's just bring it down here. And call the greet function. Hopefully, you should see something different. Oh, well, that's should that be take immutable, or will it just work like that?
No, I think that will work. It will take an exit, right? That's what you want.
Well, we want this to fail on the bottom one, I guess.
Yeah, it will.
Yeah, sweet. So that brings us on to the first point there. Yeah, that was a good point. Sorry, I'm trying to increase the size of that one. The macro is doing like an implicit borrow. So to replicate that, you're not really supposed to borrow a string like this, but I guess we can just see if it would work. We can try and do a borrow like that, and probably have to do we don't have to say it's. I thought you had to be explicit about the mutability of it, but obviously not. That's great. So what we've done there is we've made each invocation of the greet function take a borrow of the S. And that's essentially what this guy was saying the print line was doing.
But just because you created a new scope doesn't mean that accessing anything will move it from outside to inside.
Yeah.
Correct, yeah.
Yeah.
So it's the
It's
fact
only
that
function calls that cause moving
yeah,
or borrowing to happen.
yes.
And then it moved it into the greet scope, or did it move it into the inner scope?
No, it didn't move it into the inner scope, right?
Yeah, I think the point there is that if we take away this, the way I would understand it is that this is another scope.
Yeah.
So the S gets moved into that. So let's get rid of this.
Yeah.
And now it literally is gone. Like
Now greet function owns it. Therefore, it's gonna be cleaned up at the end of the function.
so Rust gets here, and then it's like right,
But what
it's going to drop that memory that applied to that S. Regardless, even something on the very next line wouldn't work here. Like we couldn't even do that as far as right now.
So
Yeah.
what if you wanted to get it back, like if you're just running procedure or something?
So the two options there are, as we saw before, like what print line's doing, an implicit borrow or an explicit borrow in our case now. You pass in a reference to it, and then providing you're not doing anything asynchronous or anything, you still essentially the first invocation hasn't taken ownership of this. It's just borrowing it for a second, and then it allows you to call it again. But crucially,
As if you borrow it, the owner is still S, the
Yeah.
first one. Therefore, Rust is not gonna clean the memory because the owner is still in scope.
correct, and then it will get to here, and that's when it would be. Where I guess in this case, because nobody's taking ownership of this S, it would be till we get to here. Yeah. But yeah, that sounds pretty good. Any more questions on that? I did have something I was just going to say. Oh yeah, the other thing was how else can I use it? So this is not always appropriate because there are other ways to handle this. Like it's a bit gross, but you can like do something with it and then return it. Yeah, exactly. So like,
Just add the redundant.
So that would work, and then you can, because obviously we get shadowing without issue, we can keep doing that. You could essentially build up. I mean, you wouldn't really write code like this because you can use like combinators and maps and stuff, but that's another way that you often see. Actually, me and Jonathan were just talking about this, in a lot of the library code you use when they use the builder pattern. This is essentially what they do to get around so many problems with ownership, is just take ownership temporarily, but then give it back at the end. And obviously, this is like, for those unfamiliar, it's, you know, it's like having a return there. Just because we're not having a semicolon there, it will return the last expression. That's another way. It doesn't look very useful there, but again, when you're chaining methods together, you see it all over in Rust. This pattern of taking ownership, giving it back in a cycle. So yeah, go ahead.
Someone else.
Oh,
I think. I was just wondering, like, how does that, like, what does that mean in terms of memory and stuff? Like, if you own something, does that mean you have literally, like, you've literally copied the memory, or do you just hold the only pointer to it, sort of thing?
So the biggest difference between Rust and most other languages is that when you pass ownership, you move the memory. So the previous S no longer is accessible. It exists, but it's no longer accessible at compile time. So the compiler checks that the original S is no longer accessed. So if you try to access S after S1's allocated,
there.
Yeah, sure. The compiler will complain that the memory is no longer usable.
Is this to do with, is this just something that, I'm trying to understand what's happening at like a slightly lower level when you move it. Is it just that it's putting it, is it literally just that it's marking the memory as not usable, and it like basically is what's stored there, so you know you can overwrite it again and move and creating another?
So I think in most cases it creates a new pointer to the value in the heap.
Right.
So the stack value is no longer accessible, and it creates a new pointer to the value.
Yeah, when you do a move, but then when they're all out of scope, I'm guessing the memory itself. Even on the heap.
All this is really just happening as analysis of compile time, so at runtime it's not doing anything special because that would make it slower than C, which you don't want.
Yeah, exactly.
Yeah, I thought so S is a pointer to hello, and then when you pass ownership, it's just creating a different pointer, so you have now two pointers, but it's just the compiler not letting you use the first pointer.
Yeah.
But the first pointer is pointing to the memory, but the compiler doesn't let you use it. That's the safety that you use. It's not that the first pointer is getting deleted or something. It's just that the compiler is statically telling you you can't do this. Although if I let you, then you will be able to follow that pointer to the memory. I think that's
So like this is the bit that goes on the heap, right? And these are just the temporary stack allocated things that point to that memory. What you're saying is, well, I guess
so that
I don't know
what I'm saying is that is the compiler telling you cannot use it. It's not that technically you couldn't use it. You could use it.
Yeah, and I'm sure like in the unsafe stuff that people do in Rust, I'm sure that they're doing.
Because imagine if you're running your program and you call read, if the computer had to copy the memory somewhere else, just so that the first pointer cannot use it, it would be very expensive.
Yeah.
That's what I'm saying.
Well, the array says that which does not implement a copy trait. The move occurs because it has a string, but it does not implement a copy trait.
Yeah, so you have types like integers who can be copied very easily. So you cannot move them, you just copy them by value.
Okay. Things that are super cheap to do, like an integer. Like there's been no reason to worry about ownership. The ownership model with integers.
When it comes to stuff like strings.
Yeah, because string is a
Okay.
I'm assuming if you wanted to, you could also implement a copy trait yourself.
Absolutely, yeah.
Make it return a pointer?
Yeah, I think
Yeah.
we can.
Yeah.
That's the cool thing about these messages. You can just read it, and it's basically pointing you in the right direction. You'd be able to implement copy for string. In fact, I think you'd be able to just, if you had a type, you'd be able to derive it, I guess.
That would make it insecure though, right?
No, not necessarily. It just means that you explicitly know that it's going to be what the copy is going to do, because you don't know if it's going to copy the pointer.
It'll just
Yeah,
mean
they
that-
are.
It'll just mean the location of the memory where the actual value is stored, doesn't it?
Okay.
I don't see how that's an issue as long as you actually secure the memory itself.
Yeah.
Although one thing I'm wondering about now, a slightly different tangent from that, the point we were talking about before, where when you move it, the original pointer value is still on the stack for the previous frame, the previous function. It's still there on the stack. I wonder if that might be some sort of, if there might be a security concern from that.
Maybe that's
Just giving someone ownership to a variable at some point means in physical memory the value is still there, but because Rust stopped you from being able to use it. I don't know if that makes sense. As a pattern. Yeah.
that's fine.
I have a feeling that you can't just implement copy for things that live on the heap, because they're unsized, and so then you come up against this problem where you can pass ownership to multiple things and then not clean up the memory.
Couldn't you copy both, or create a new pointer but copy the data? The pointer is pointing to this new data you got here.
Yeah, I think you could make it safe, maybe. I don't know.
Cool. Let's carry on.
But
There is another book that goes into detail on that specific topic of memory. Yeah. Big one, but I just don't know.
I think the alternative is just use clone, right?
Yeah.
Which is opting into the expensive operation of clone, rather than pretending that it has copy and using clone.
Yeah, because I've seen some of the stuff I've written. Sometimes values that you have will get moved into a closure, and as long as you derive clone on your struct, for example, it's normally can figure it most of it out for you.
Right.
Have you ever done that? Like just derive clone on top of anything? So like, because if you have a closure let's say it's going to end up running in another thread. If it, like you say, if it's a simple type like an integer, it will just, you won't even have to do anything. Rust will just copy the value in there for you. You don't have any issues. But then the moment you try and do anything else, you have to put derived clone on top of like a struct, for example.
Okay.
And it can often do that bit for you.
But clone's obviously safe, not. We're talking about copy up.
Right.
Which is more about the memory. I don't know. Want to look up in it.
Yeah, for sure. So let's crack on. So string literals are convenient, but they aren't suitable for every situation in which we may want to use text. And one reason is they're immutable. Yes, see, I got that right. Another is that not every string value can be known when we write our code. For example, if we want to take user input and store it, for these situations, Rust has string, which is what we just saw here. So the main difference, obviously, as we saw, string can be mutated, and we use that method. It's great.
So, sorry, the string itself can be mutated. Can you do let s without the mute and it still be mutable?
Not in this scope. So let's do an example. So that's the demo they gave us. You're just asking what happens if we remove this mute, yeah?
Yeah.
Well, that would definitely fail because
Yeah, then it can't be.
even my editor's telling me before I even try and run it. Cannot borrow immutable value. Yes. What is quite interesting, I guess, is I'll never know the answer to this straight away, but if that is immutable there, what happens if you wanted to run that in a separate function? Would you take it mutably? This is where it comes into where you put that mute keyword.
You should, yeah.
Again.
Oh, maybe not.
I see. Sometimes these things seem so simple, but it's
I mean,
like,
you own it, right? So you should
I
be able to give a mutable reference, but I think you're right. I think it can't.
well, let's just see. So if we call mutate, go to that, mutate on S. Sorry, yeah. Maybe I should just call everything S. Yeah, so this is where expect a string. Oh, sorry, yes, because that doesn't return the string. So I have to return the S like that. Now we're going to get this thing, and this is what I like about it. Well, not like, but this is what I was surprised by, is that even though we didn't declare it as mutable here, really the mute keyword is not, it's not like you're changing this S forever. You're not declaring some rule on it that it can't be mutated forever. You're just really saying in the current scope, because as the compiler is telling us there, you can make it mutable inside there. Weird, right? Not weird, but that's just interesting that the way it's presented is that you're declaring the mutability of the variable here in the first declaration. But you're really not, because it's just really to do with the scope that I've highlighted there. Once you give it here, you can mutate it just by putting this character, this mute keyword there. So that's quite interesting. I think you can also do it.
If you do let S is mutate S, then you can mutate it.
Oh, if you do let mutable, then you cannot call the mutate function method, because then you will be breaking the rules having two mutable references, right?
Well, no,
Yeah.
because he's passing ownership to mutate.
No, I mean if he
But still,
are you passing
so that-
ownership?
sorry,
If you put mute in front of S in the mutate function,
what, take rid, hang on, where?
No,
In the
it's
signature here?
that's not a reference, is it? Yeah.
That works.
That's going to work, but it's basically saying you didn't need to say it here. That's what the warning is.
So then that's
But if you were to pass by reference, it's always mutable.
Okay, yeah. So mutable to start with,
Yeah.
pass by reference. Then we would have to change the signature here to be
That should fail, right?
hang on, what's wrong there? So found reference, consider borrowing S. Oh, sorry, it's because I've put that in the wrong place. It should be here. And now we've returned a reference, so we just do that. That's not going to work. Cannot borrow.
You already have a reference, right?
Yeah. Basically, this is, yeah,
Yeah, so you cannot have to mutable reference that.
correct, yeah.
No, you're using the wrong
You mutable reference to S because you're mutate ampersand S rather than ampersand mute S. And you're making a mutable binding to an immutable string by the looks of it there.
Change and to unmute.
Or here.
Yeah.
No.
Yeah, both places I think.
What there?
There.
So
Just look at the compiler.
it's thinking mutate function signature, you want S ampersand mute string.
It's complaining about the that signature. Yeah.
Confusing in the take.
That's it, yeah.
So
Hang on.
And then you are returning. No, that was okay, I think.
Types different immutability.
That's it. And then you are returning a reference from the function now. That's why it's complaining about.
Found mutable reference. Okay. So how do we get around this? Just make it.
Yeah, just return the reference, right?
So it's saying the return type of the function isn't what you're returning.
So,
Yeah, just return a mutable reference. Yeah, like that.
oh man, so much code. So like, that's just token soup to me.
So that works.
Completely. Yeah, but it's,
that there that you highlighted, I think, because of the function signature declared.
No, but he just compiled, okay.
oh no, it has to be like
No, like that, yeah.
Yeah, just ampersand.
It's fine like that, just run it.
that. That works.
Yeah,
Yeah.
And what? Move that.
Done that, yeah,
No.
that should work.
No, because then you're passing an immutable reference.
I agree.
You always see whether that is going to be changed, but.
Right, but it works in reverse, doesn't it? Where a function returns a mutable.
I think the best thing is to just not do any of that. One thing I found writing some programs in Rust, it's like if you find yourself doing stuff like that, it feels wrong because it probably is wrong. Like it's or not wrong, but there's probably an easier way. So if we just take in, surely that just works. There you go. And actually, we don't even need that. So we're back to what we had. It's simpler. And you're just declaring that for the lifetime of this current function body scope, the S that you've taken in is going to be mutable.
Well, yeah, I think it's less common, but it's not particularly wrong.
Not wrong, but
Like passing mutable references, and it's
So,
more of a low level thing.
yeah.
so sorry, just a second. let's take a breath for a second. So I'm still slightly confused about the fact that like you have a string that has a function on it called push stir, but like if aren't all variables supposed to be immutable by default? So if you don't specify mute, suddenly you can't use that function push stir.
Yeah, it's actually taking as the first argument ampersand
String,
mutable.
Self, yeah.
So it's actually demanding a mutable reference.
Right.
So if you have an immutable variable, you cannot provide that mutable reference.
You
There you go.
actually
So
see that.
that would make it fail.
So that's why, yeah. So it's taking a reference, yeah.
So it's our immutable. Okay.
And obviously, you can see that obviously underlying a string is just a vector.
So what was that thing that was going on? Because I kind of went over my head about because you put mute before the S, and then you also put mute at before string. Do those two mean different things?
Yeah, I'm not exactly. Yeah, I couldn't articulate what's different about that. Does anyone else want to take that? Like, I know what you mean. You mean it like you put it here, but then sometimes.
You can put there, it means something else.
I think if you put it in the beginning, it means you're taking ownership, right? You're taking owner. S is now the owner, and it's a mutable binding. But if you're gonna take a reference, then you have to put it on the right hand side. Like you cannot take if you put an ampersand in there. That doesn't mean I don't think that would work because you're not taking ownership, and that's confusing because that doesn't mean you're taking a mutable reference.
So one is basically a type definition and one is like a variable ownership definition.
Yeah, I think so.
Yeah, it tends to be the things to the right. Yeah, this is the type. And this is like
That's
a
just a
modifier.
variable binding. Yeah.
Yeah.
Variable definition.
Who would have thought that someone was to speak about the strings, right? In the case of a string literal, we know the contents at compile time. So the text is hard coded directly into the final executable. So what it just means there is that when you do with any string there, the thing in between the two quotes, it just puts that into the program. There's no messing about it. It's there, it's immutable. It's just a value that can be accessed in memory.
Probably in a read-only part of memory, like they do with C or C++ as well.
I'm sure. And it says this is why string literals are fast and efficient. But these properties only come from the string literal's immutability. Can't put a blob of memory into binary for each piece of text whose size is unknown at compile time and whose size might change whilst running the program. Unfortunately, yeah. With the string type, in order to support a mutable, growable piece of text, we need to allocate an amount of memory on the heap known at compile time to hold the contents. So this is like, to bring it back to something like JavaScript or PHP, we kind of get all this stuff for free, don't we? That we just create a string, we can make it 1 million characters long if we want, or 1 character, and we don't think about the memory that's involved with it. It's quite a nice property, actually. But in Rust, we need to think about that. And it says here that in order to support that, we need to allocate an amount of memory on the heap, known at compile time to hold its contents. This means the memory must be requested from the operating system at runtime, and we need a way of returning this memory to the operating system when we're done. And the first part is done for us when we call string from. So I think what it's saying there is that string from, allocates a request from memory. Its implementation requests the memory it needs. This is pretty much universal in programming languages. But the second part is different. In languages like with a garbage collector, the GC, short for garbage collector, keeps track and cleans up memory that's not being used anymore. We don't have to think about it. Without a GC, though, it's our responsibility to identify when memory is no longer used and call code to explicitly return it. Doing this correctly has historically been a difficult programming problem. If we forget, we waste memory. If we do it too early, we'll have an invalid variable. If we do it twice, that's a bug. We need to pair exactly one allocate with exactly one free. So Rust takes a different path, and the memory is automatically returned once the variable that owns it goes out of scope. So back to that example before, it's basically saying that by the end of here, it can clean up the memory that S took because no one's using it anymore.
But basically, Rust removes use after 3 hours, which is like 9% of all security bugs in C++.
Yeah, I guess that's why they speak so heavily about safety. So there's a natural point in which we can return the memory. Yeah, there is a natural point at which we can return the memory our string needs to the operating system, and it's when the S goes out of scope. Sounds so obvious, right? When a variable goes out of scope, Rust calls a special function for us. It's called drop. And it's where the author of the string can put code to return the memory. You very rarely see drop. I actually had to use it doing some threading stuff. Literally, it's like a global function that you can just call drop on. Like that. If it gives an example of why you need that. This pattern has a profound impact on the way Rust code is written, because it may seem simple right now, but the behavior of code can be unexpected in more complicated situations when we want to have multiple variables use the data we've allocated on the heap. Anyone want to say anything about that chunk I just read? No?
I agree, it gets very complicated.
Yeah. So the ways variables and data interact. Multiple variables can interact with the same data in different ways. Let's look at an example using an integer enlisting for 2. So we can, okay, let's just read this as it goes. So it's doing bind the value of 5 to the variable x, then make a copy and bind it to y. We now have two variables, x and y both equal 5. And this is indeed what's happening because integers are simple values with a known fixed size. And these two 5 values are pushed onto the stack. That's quite an important bit there, I think.
So you don't clean memory from the stack, right? Just when the function finishes, it goes out of scope. So therefore, the rules don't apply in here.
Yeah, and I think also like the ownership, some of the ownership things don't take effect because they don't need to, because it's so cheap just to give y the value 5 as well. What would happen if you modified y to this case? You wouldn't be
So
modifying
y
x
is now its own thing, right?
Yeah, but it's
It can
because it's
divert from.
cool.
Do anything that implements copy have mutable methods?
Anything that implements copy, you have mutable methods.
So
I genuinely don't know.
integers implement copy because they're small and they're sized, right?
Mhm.
Do they implement methods that mutate? I don't think they do they?
I can't think of any like
So when you
y.
do 5 plus 5, you're not incrementing the variable itself, are you? You're just copying and then creating a new variable.
Do you mean in
I
context
think so, yeah.
of this one here?
I would imagine so, yeah.
Do you want me to run a code sample or
No, I was just interested if you knew.
I don't?
Oh yeah, like if you do, if you do 5 times x, and you don't assign it back to x, and then print x, x will still be.
Oh yeah.
That's an actual. The operation doesn't change the
Yeah.
variables themselves. I don't think.
So if we look at the string version,
So is it that you can't ever write codes that changes a value of an int without copying it? Well, you'd have to pass it somehow by reference, I guess, if you could.
Yeah, I think so. I think.
Well, even if it's mutable, it would copy it, right? Or would it?
Yeah.
It will still copy it unless you say I want a reference of that explicit like variable.
You
It will
have
just
to
make a
sell-
copy of the number. So I'm just wondering if anyone could someone write a function that's called like I don't know, a function called dot product, which takes two numbers, and actually is it actually possible to change those two numbers like at all, or is it that integers just have a specific implementation?
I've got a feeling you couldn't modify them personally. Like, because they're going to be immutable, just like that string slice that we saw.
Yeah, because they'd all have to be mutable references.
You can change what a variable points to, but you can't change that actual integer. I think. Might
I
be
guess
wrong.
in that point you will have to create your own struct. Number with nothing inside.
So if we look at the string version, it looks freakishly similar, but it's very different. And we might assume it works the same way. Sorry. So we might assume that it works the same way. So we might assume that the way it works would be the same. That is, the second line would make a copy of the value S1, bind it to S2, but this isn't what happens. So here we can see a string under the covers. The string is made up of three parts. Shown on the left is a pointer to the memory that holds the contents of the string. Is a pointer that holds pointed to the memory that holds the contents of a string, a length and capacity. So this is on the stack. This group of data is stored on the stack. On the right is the memory. On the right is the memory on the heap that holds the contents. So I think the point there is this thing on the left will never change in size. This could be like a few characters, or it could be thousands of bytes. Doesn't really matter. So it wouldn't make sense. We talked about before that this creating a copy because it's so cheap to do so. Imagine if this is a whole book worth of a string. You wouldn't want to copy it and double the memory every time just because you allocated a new variable.
So I think it's copying that part on the left.
Yes,
the
which
pointer,
is
the length, the capacity. It's copying that, but you still have the pointer is still pointing to the same piece of memory on the heap.
yeah. And I think in this case, actually, S1 would be invalid now. I think because of the ownership rules. Like S2 now owns that piece of memory, but I think we get to that in a second. So yeah, so this is the representation in memory of a string holding the value hello bound to S1. So we see the S1 just above there being the variable name. The pointer being, like literally a directions to go and find that memory on the heap. A length 5 and capacity 5. What's always not worried me, sorry, my lack of knowledge is when we say this bit's always a known size, it's like, well, how can it be a known size? Because this number might grow very large. That bit's always, if anyone wants to explain that to me.
I think when you see that maybe you need to store the structure to tell you what the number is, it's always the same because it's always 64 bits.
Right. Yeah, that would make sense, yeah. So it's the size of the integer that's used, like in terms of, sweet. Okay, so the length is how much memory in bytes the contents of the string is currently using. The capacity is the total amount of memory in bytes that the string has received from the operating system. That's interesting, so you may not get enough. Difference between length and capacity matters, but not in this context, so for now it's fine to ignore the capacity.
I think usually it would give you at least as much as you need,
Okay.
or it will just tell you there's not enough memory.
So take the string in Rust is now to just allocate more memory for you whenever it needs it.
Yeah, it's kind of, that's what the abstraction's there for, I guess. To be growable.
For the internal implementation of it to refer to rather than you need to look at from the outside.
Nice, and then we see here that when we declared this S2 equals S1,
So different pointer, but same data.
yeah, I think that means, if that's correct, that means that, so I was wrong. So how does,
No, but S1 is now invalid.
oh, sorry, yeah, so this is just showing you
That's
that
what I meant, like
this diagram,
that's what I was talking about earlier. There are 2 pointers pointing at the same data, but
Yeah.
it's just Rust telling you cannot use S1.
And going to that.
It says it makes a copy of S1, so I would imagine it's still valid.
Yeah, but Rust will stop.
It's
you.
technically it's the
It's
compiler that even
valid in
before your
terms of-
program runs, the compiler won't let you use it.
yeah, you'll never be able to compile it.
Right, okay.
It keeps track of that, of when you move ownership. Somehow it keeps track of that.
Yeah, it's literally single owner forever for
And
everything.
it stops your program from compiling at all.
I think this diagram is a bit confusing. Like, I think they should have said like this is now invalid. Maybe
I think they go, yeah.
Yeah.
There you go, I think, probably.
This says the S1.
Oh, if Rust did this, the operation.
Oh yeah, it's cool. Yeah, so it's basically saying that's a terrible pattern.
Okay, yes. Explain more.
So
Does not look like, okay.
figure 4.3, which was, let's just get this right. So that's 4.2. Yeah, 4.3 is this one.
Oh, okay.
What would it look like if Rust instead copied the data to the heap as well? This is what I was saying before. Like every time you reassign that, it's not going to copy the memory that's on the heap. If Rust did that, the operation S2 to S1 could be very expensive in terms of runtime performance if the data on the heap were large. Obviously, with just hello string, you're not going to notice anything, but it's obviously just a bad idea. Oh, so actually it's saying that this is another possibility for what it might do. Yeah, of course, yeah. So that's doesn't do this either. Earlier we said that when a variable goes out of scope, Rust automatically calls the drop function and cleans up the heap memory for that variable. But figure 4.2 shows both data pointers pointing to the same location, and this is a problem. Because when S2 and S1 go out of scope, they will try to free the same memory. This is what Jonathan was saying, it's a double free error. And it's one of the memory safety bugs we previously mentioned. Freeing memory twice can lead to memory corruption, which can potentially lead to security vulnerabilities. If anyone just on that topic, I've just remembered, what was the huge Cloudflare one that was about a year ago? Does anyone remember that? I think that was literally a bug. So basically they were leaking certain chunks of memory through one of the, obviously they do CDN.
Yeah, this is Amazon.
No, this was like Cloudflare, which is a huge portion of the internet. And apparently they were,
Yeah, like every image was like on every website.
well,
Yeah.
probably,
that
yeah.
was the
But
bug. Yeah, I remember that.
I just remember specifically it being some kind of memory related problem.
A lot of people are laughing.
Can't remember the details of it, but if anyone wants to pull it up and have a look, good one. So to ensure memory safety, there's one more detail to what happens to the situation in Rust. Instead of trying to copy the memory, Rust considers S1 to no longer be valid. Therefore, Rust doesn't need to free anything when S1 goes out of scope. So check out what happens, and yeah, if we were to try that, might as well just do it because we haven't been in the editor for a while. So use of moved value S1.
I
S2
think the
is,
compiler is really helpful, that message. When it says value moved here,
yeah, that's,
so that the ownership is changing there.
yeah,
And then you try to use the value after it has been moved.
yeah. So this now owns that memory on
So
the
it's just the compiler like enforcing you.
Yeah.
Not using.
Sweet.
Copy it then between essentially you have to rename.
So you get an error like this because Rust prevents you from using the invalidated reference. Yeah, that's what I love. The compiler is so good, and if you've got an editor that allows you to click through, like when I was refactoring quite a big program the other day, I can just keep running the compiler and just click on it, every error, fix that error, go through. Especially like, yeah, because this takes you straight to it. Yeah. So yeah, Rust prevents you from using the invalidated reference. If you've heard the term shallow copy and deep copy whilst working in other languages, the concept of copying the pointer, length and capacity without copying the data probably sounds like making a shallow copy. But because Rust also invalidates the first variable, instead of being called a shallow copy, it's known as a move. Here we would read this by saying S1 was moved into S2. So that's kind of the terminology. Saying S1 was moved into S2, yeah. So now there's only one pointer to that place on the heap. And that solves our problem. Now only S2 is valid in this scope. So it's like, this is literally pointless at this here.
So Rust is smart enough to only call free when S2 goes out of scope now.
Yeah.
It doesn't call free for
So it's going to
S1.
be, yeah, it's almost like they insert this.
I think down in the chapter, it proves it by calling, you can see where it calls drop, right? I'm not actually sure.
In addition, there's a design choice that's implied by this. Rust will never automatically create D copies of your data. Therefore, any automatic copying can be assumed to be inexpensive in terms of runtime performance. That's what we talked about before, where integers can just be copied freely between threads and anywhere, whereas more complex data structures require you to figure it out or derive the right trait. So the ways variables and data interact is with clone. If we do want to deeply copy the heap data of the string, not just the stack data, we can use a common method called clone. But because methods are a common feature in many programming languages, oh, sorry, yeah, that's just saying that the syntax is, yeah. So that's the example. Let's just copy paste it. Pretty simple, but this means that we've still always got access to both S1 and S2. Clone creates a new item on the stack that has memory that was identical to whatever that was, but it's its own memory. So there are now two bindings to two pieces of memory. That should compile perfectly.
So if you were to change S1, it doesn't change S2.
What, you mean after the fact?
Yeah.
So like S1. Yeah, because it's at that point in time when it was cloned. It's not like it's not looking at it for all future references. That's actually a real source of bugs. Like in JavaScript code is a great example of this, where almost everything is passed by reference. Not necessarily, actually, weirdly, not strings because they're immutable, but every other type of data structure like arrays and objects, you pass them around, and yeah, you never really you can modify something underneath someone else's.
Out of interest, how does object equivalence work in Rust?
That's just with the your type can implement the trait, can implement the equal trait or the partial equal trait.
Oh, so you still got to override the functions, the object equivalent. Like in Java, you'd override the equals. Yeah.
Well, yeah, but you don't.
Yeah.
So if your types both implement the equal or the
trait.
yeah.
You can do it. You can do it.
Which is that you can actually just write to the structure derive e cube, and the compiler will just write this implementation for you.
Yeah, so I'm guessing so string already has the string has already implemented it. So like.
So when you do if S1 equals S2, I think what it's doing is S1 calling a method on S1 called equal.
Yeah.
And passing S2 as a
think
parameter.
Yeah, it's
And
like,
you can override that method
yeah,
or define it
That's,
for you.
that's one dot each. isn't it?
it's gonna be, it's what?
It's 1.8, yeah.
What
You can call it directly like that, yeah. You see?
You get it as a function and then pass S2 inside it, and then ignore the whole.
That's basically why it's doing.
So the other's just. a
Yeah, but even,
version.
yeah, but that's also, you should go to the equal
Yes.
trait method with pattern in S1 and S2, I guess. But anyway. Oh, hang on, expected reference. All right. So yeah, you
It doesn't take
take-
ownership of that. It just takes ownership. Hang on a minute. Yeah, that's equal.
But what I'm saying
If
is,
you change it, it won't be equal, of course.
it's like with add. Like you can implement the add. You can implement the add trait for any two objects, for example. So like you could have two things. If you're doing graphics or something, you could have two structs that represent coordinates or something, and you could implement the add trait for that struct, and then you can just do like 0.1. This was like a complex struct. What's 0.2? You can totally do that. It's not like operator overloading. It's more that you're just implementing the add trait. Does anyone else want to expand on that? Because I know that's correct, but I don't know the exact terminology to
I
explain
think
it.
it is overloading, but just for a defined set of characters rather than other things that. Like,
But you can't invent your own you can't invent your own symbols there, for example. Like you are literally just providing. You're providing an implementation of the add trait.
Yeah. So add basically means an add trait.
Sweet. That's how equal works as well. You're just implementing. And just to go back to that example, that's
Oh, implement it for one struct.
yeah.
It's so fun.
Well, first of
So
all,
you can see like
see.
the syntax of creating an object and implementing a trait.
Okay, so let's have a point X. Oh, we're thinking of examples, so there you go. Try to do equal comparison on those. What's going to happen? You see, so this is where, so to make that work, we need to implement the partial equal trait point. The easiest way to do that is to derive, because it's this, it's this. Rust can implement this one for us basically. We say partial equal, and there's a few of them that standard library give you.
Probably worth implementing ourselves. Right?
Yeah, I'm just showing that. Okay, yeah, so that wasn't equal, and now it is. And what was the namespace again? So
If you need to do it, then free.
I'm not sure. So if we say impl point,
Oh no way! That's it. That's not work.
It's cheated.
It's done.
wow, cool. So that trait has a actually, I guess we don't have to do the other one, but yeah, so we get access to self and we get the other. So we know that point has a X property.
Well, what's the other type? What's RHS?
Right.
Yeah,
So
now.
you have to make the associated origins.
Associated type, isn't it?
Yeah,
You
but
open
is
the-
that
The documentation.
Yeah.
it's because it's generic on the trait there. So would we have to do that? I don't know. Someone jump in. I think
Open the documentation, I would say.
that was the documentation.
No, I mean like the Rust docs. Isn't it?
This is what the Rust doc's built from.
I mean, yeah, but it's.
Oh, sorry,
hard to read.
it's hard to read. Sorry. How can I implement partially? Hang on.
Oh yeah, there you go at the bottom. Yeah, yeah. Just put the. Yeah, you say in book there. you can just change it with your own.
So you can just change the signature in the actual function in the method there. So we don't need to make that generic there.
Oh, yeah, I think the point is that,
The function is
You can do
generic.
anytime.
yeah, you can do anytime.
You can,
Oh yeah, so you could compare a string to a number, for example. Yeah, sweet.
or you
Or any complex, yeah, anything really. The point is that I guess this is the left hand side. If you think of something like when you're doing it equal, when you say equal partial equal for this point, you're saying the thing on the left hand side, and that's why the variable was named right hand side. So self.x and x. That'll be it. That'll be how. There you go.
can you do like self x plus 1 equals other dot x, just to make sure that it's using your stuff.
What do you mean?
Just do self x plus 1 there. Yeah.
Yeah.
Oh, but you will copy it, right?
What are you trying to check there? Because it's like the
I'm
fact that
trying
you're
to-
implementing it for point means that that's self here is definitely a point like. What
No,
is it?
I'm trying to, because you don't know if it's using your trait, because.
Oh, sorry, here. You want me to change the
Oh,
value?
okay,
here?
yeah. No, I guess it doesn't matter. Yeah, it doesn't matter.
Yeah, you can see if I just do it else.
I guess you can implement it for another type now. It would be a different implementation block.
Yeah, you wouldn't be able to do because you can only define a method once.
Oh.
So if you wanted to compare, oh yeah, so we could
Would that
do
work? Yeah.
want to implement it do it for a string.
Or no, did you want to compare like a point with a number,
Yeah,
for example?
Just a point, yes,
A point with another what?
A number.
with a
just
number.
Yeah, that's what. Oh, a number. Yeah. So like.
So that should be point, right? No, that is.
Oh, sorry. Yeah. So point here because that's the left hand side, and then you could you'd have to.
To E32.
I don't think this would this
You
even
can
work.
make them generic.
Yeah.
That's why I was wondering.
Okay, well, let's try it because I genuinely don't know. Hey, what? Are you 32?
Yeah. Oh yeah, yes.
So you want to see if that works?
And then other, when you say other, you don't have to do other.x. Just remove the x.
Yeah, just do self.x and equal to order.
Yep.
Yeah, and then p is equal to p2.x.
The implementation does the same thing. I think you need square brackets there.
Square.
on the bottom line.
Yeah, right angle brackets, like you're doing.
Yeah, that's what I thought. Because when you looked at the implementation, it was generic over it had one parameter. there.
Oh yeah, that's it. Yeah.
Yeah.
I guess Rust inferred that type.
So look, so it's because it's using associated type. So basically, it's saying that you can either put in something that may or may not be sized, or this is like saying, if you don't provide something, I'm going to use the associated type. And if we look at
self.
Self is point.
Self
Yeah.
is point.
self is the thing you're implementing it for. So that's it. That's why it works without the generic. But then I guess are we saying that if we do this, we
point
should,
there at the point when you want to do two. So you need U8 at the bottom.
Yeah, you could actually omit it from the top one.
I don't know if you can at the point when.
hang on. So
Yeah, that should be fine.
So at the bottom one, put
this is what didn't work a second ago. Yeah,
Yeah,
that
but
doesn't
the
work.
second
bottom
one,
one needs U8.
the
That's
bottom
a
one,
generic.
yeah.
Oh, just make that.
Yeah, that should work. Oh, maybe. Oh, it needs to be a.
Consider dereferencing the borrow.
Yeah.
Hang on, maybe that doesn't need to.
Yeah, dereference.
Sweet.
Yeah.
Wow, nice. Yeah, I've not really done that before, where you like implement the same method for nice.
So now if you do p is equal to p2.x, that should work. It should use your second method.
Oh, nice.
Yeah. Okay.
Yeah, that's so cool. Awesome. That's a bit of a divergence, but a good one. That's what I mean. That's what I love when we do that.
That trait part is in advanced traits.
Oh yeah,
It's like chapter 14.
Yeah, that's all right. There's nothing wrong with that. Deep diving a bit. Oh no! Right, sorry, gotta do that again. Just making a bit of a disco. Intro again. Where were we? So yeah, we just talked about cloning. How the hell we got onto traits from there, I don't know.
You call it.
Or implement. In fact, it was Diego said, let's implement our own. I was just going to do derive.
Yeah, but anyway, right?
I was like, bro, derive does the job. Right. So stack only data copying. There's another wrinkle we haven't talked about. This code uses integers. This code using integers, part of which was shown earlier, is valid and works. Yeah, we talked about why that was okay. But this code seems to contradict what we learned earlier. We don't have to call clone, but X is still valid. It's because types such as integers have a known size at compile time and are stored entirely on the stack. So copies of the value are quick and easy to make. I'm going to script through some of that, because we talked about it in depth. Rust has a special annotation called copy trait, which you can place on types like integers that are stored on the stack. If a type has the copy trait, an older variable is still usable after assignment. Rust won't let us annotate a type with a copy trait if the type or any of its parts has implemented the drop trait. All right.
Yeah, so that's why I was saying earlier. You're not allowed to implement copy when you implement drop, and you need to implement drop if you have stuff on the heap.
Okay. Sweet. Yeah. So it's the type system basically enforcing all of that. If the type needs something special to happen when it goes out of scope, we can add the copy annotation to that type. We'll get a compile type error. To learn about how to add the copy annotation to the type, see derivable traits. And we've kind of done that already. So what types are copy? It's weird. That's just like that phrase there is. They say like what types are copy. It doesn't really make like. It just basically means what types implement the copy trait, I guess. That's right, yeah? But like that little phrase is often how you hear it. They'll say like what types are sized.
Yeah. Or
which sized makes more sense because of the word. But
is it debug or things like that?
Yeah. You can check the documentation, but as a general rule, any group of similar scalar values can be copied, and nothing that requires allocation in some form of resource is copied. Here are some types that are. So you've got integer types such as U32, the Boolean, which is going to be true or false, floating point numbers, character type, tuples. But obviously tuples, the restriction there is that inner types have to be copied. And it gives an example there where you could have an arbitrary tuple you could have a tuple that contains two values, an I32 and a string, and that wouldn't conform to it being a copy because of string obviously needing data on the heap. So, we're really getting through this and on time as well, so that's good. So now we get to ownership and functions, which we kind of touched on ourselves already. The semantics for passing a value to a function are similar to those for assigning a value to a variable. Passing a variable to a function will move or copy just as assignment does. And that's what we saw before when we called that greet function. List 4.3 has an example with some annotations showing where variables go in and out of scope. That's pretty hard. Let's bring that into the editor, see if it's a bit simpler to read. Probably harder right there. So yeah, the first bit, the S comes into scope. The moment it's used in a function call, it's no longer valid here. But it's not the function that decides that, right? It's how you.
No, it is though.
It's how you pass. Well, it's not, because if you want to pass a reference, you do it.
You can't, because the function.
Oh, sorry, yeah. So the signature, yeah.
Demands something.
Oh, sorry, yeah. So I guess, yeah. So it's exactly the opposite of what I said. Then. Yeah, you're right. Like the type of the method or the function indicates how you can call it.
Yeah.
No longer valid here. X comes into scope here.
So if you have like some library where someone's written a function that takes something that's mutable, but you don't want to change your copy, you have to clone it.
Yeah.
Give it that second one.
Yeah. You tend to see with like most libraries, it's like they'll either enforce that you give a reference, or it's when you're doing like the builder pattern, so you end up with something back at the end of every method call. But yeah. Same again, X comes into scope there, make a copy. Oh yeah, and then this is making the point we just read about. So because this is a simple value, it's just the I32. Rust is not going to move this X into ownership of this. It's just going to give it a new 5, basically. And X is still valid. Prove that just by saying use. X. Yep, and we get no errors. I think that's pretty straightforward. We've covered almost all of that many times already tonight, so I don't think we need to dwell on that too much. Any questions on that one? It's just really the difference between string being on the heap and therefore needing to abide to the ownership rules, and X being a simple value and not needing to. Or basically ducking out of it because it's copied. If we tried to use S after, yeah, we saw that. And now return values and scopes. So let's just look at this for a second. Oh yeah, this is very much like the example we did before. So in the editor. So S1 here calls this function that returns a string. The string is created inside this function, so it would normally only live within these curly braces, but because I have it as the last expression in this function body without semicolon, it's returned as the return value.
Also, you remove ownership and then
Well-
Rust doesn't call drop, I guess. Yeah.
Well, I guess the thing to drop here would be like this stack frames reference to that, but then this would be a new. So each function body is like it's going to be a separate stack, a separate frame on the stack.
Well, it doesn't really matter if it drops it. It will drop it anyway, right? When that function finishes, gives ownership.
But what I mean is you're talking about two different frames here.
That's what I mean. Like there's the frame of gives ownership. That's gonna wait anyway.
Yeah.
So it's gonna make it.
But it's returned, yeah. So it's returned an S1 here, which lives in this stack, this frame of the stack. S2 is just a new variable binding. Oh yeah, so this is the pattern we looked at. So it's like something that takes ownership but then gives it back. Again, this is really common. So by calling the function, it's not a reference look, so it does move the does change ownership. Then this is like a new frame on the stack, so it does whatever work you're going to do with it, and it returns. In this case, the same thing, but it could be like mutating it or whatever. And then you just back to S3. And I think it's quite a nice pattern actually, because it removes so much of the borrowing and other little bits of syntax you have to put around the variables. If you can get away with it, you can't always do this, but quite nice. Any questions? I feel like we've covered this quite extensively in other bits, but
Yeah, so I think what's looking there is it gives ownership. I guess it kind of proves that you can't get yourself into a problem like with C and C++. You can create you can sometimes like mistakenly create a variable inside of a function and then return it thinking that the thing that called it is going to get it. But No, okay. I think I take back what I was going to say.
That's all right. Sometimes when you say it out loud, you resolve it yourself.
Yeah, I was thinking. So I can't remember how it happened, but I'm pretty sure I remember at some point that I had made a mistake where, like, inside of a function, I created a variable and then returned it, and thought I had gotten it when I went by returning, but I hadn't. So
Yeah, don't think those
I
types of
don't
errors.
think you can do that in Rust because it will just move the ownership.
Exactly. So, yeah, so I think that's pretty.
But ultimately, it's not clearing some string, I think, is the main demonstration. So, like, some string belongs on the heap and the stack.
Oh,
The-
yeah.
For this frame, but then
The
when this.
stack part gets removed, dropped, right?
Yep.
But the heap ends up with a moved new part on the stack.
Yeah,
So it doesn't call, drop is never called for some string.
Yeah.
Because Rust realizes, oh, this string, this function is giving ownership to someone else.
Yeah.
So I'm not gonna drop this value.
It only copies the sum string, like string.
yeah,
Like say copy, move this one.
Yeah, moves the pointer to the string on the heap.
The pointer and the length and capacity.
Yeah.
we did pretty well with that. And then, yeah, that just basically goes over transferring ownership of return values, which we just talked about. When a variable that includes data on the heap goes out of scope, the value will be cleaned up by drop unless the data has been moved to be owned by another variable. Yep, that's what we talked about. Taking ownership and then returning ownership with every function is a bit tedious. What if you want to let a function use a value but not take ownership? That's what we've covered as well. It's quite annoying that anything we pass in also needs to be passed back if we want to use it again. In addition to any data resulting from the body of the function that we might want to return as well. It's possible to return multiple values. Yeah, so here it's showing you that you can get that ownership back. Let's just copy this in. This is a pattern. This is not as often used. Actually, it is in a lot of the methods on options and results and stuff. But
It's kind of using it to make the point that it's not nice.
yeah, that it's extra work, it's extra syntax, extra typing. Like it's just extra things to think about. Obviously, the type safety still occurs. So because this tuple is strongly typed here, you can't get it wrong. You have to return a string in the first position and the U size in the second position, so that when you destructure it up here, you're getting what you expect. But it's just for most in this case. And it's just saying it's too much ceremony, a lot of work for a concept that should be common. That brings us on to references.
Oh my God.
That was long, right?
Yeah.
But that was good. Any questions on this?